So instead of really introduce this PDE, so the main purpose of this talk is like introduce the analysis tool to which would be possibly useful in analyze PDE. So yeah, I chose this topic partly because it's hard to shrink the tool into one sentence and put it as a topic. But still, as promised, I will get to this PDE when approaching the end of my talk, and at least show you how it's rewritten and why it could be possibly useful. So the first part is pretty relaxing, so you can enjoy the food as well as it will be preliminaries about analysis. So first of all, I want to say a little bit about complex analysis, which I will use later in the talk. So first of all, I want to remind you the notion of holomorphic function. Okay, a function is holomorphic at a point means it's differentiable in terms of the complex variable, or like it satisfies the Cauchy-Riemann. So a holomorphic function f plus ig, where f is, I am gonna only get f to r, which is to r, where the c minus is the lower half plane. So x plus iy, y less than 0. And the Cauchy-Riemann equation is x derivative of f equals to y derivative of g, and y derivative of f equals to negative x derivative of g. Right. And what else do I need? Okay. So, and also by Cauchy-Riemann equation, one can easily derive that both f and g are harmonic functions on R2 with spatial variable x and y. So, or in other words, Laplacian f equals Laplacian g equals to 0, c minus. Okay, I think that's all I need from complex analysis. Oh, yeah, but by the way, so f and g are a pair of conjugate harmonic function. And if f is given, I want to find the other one. It's unique up to a additive constant, right? Because the way you find it is you could consider x derivative and integrating y, and you will have an additive constant coming from an equation. Okay, so that's all for content analysis. So let's get down to the real content now. So the first question is going to be, given a function, okay, it's the nicest you could ever think of. So it's infinity from R to R. So it's actually a function that's defined on the real y. I want to somehow define this harmonic extension. Means does there exist a harmonic f which is c minus 2r such that the restriction of f on r equals to f. Okay, so, and the answer is yes, because this is the first question in the talk, right? If it's no, I would have nothing to say. So, okay, why is it yes? Because, okay, I need to define first of all this function called Poisson kernel, which is a collection of functions depending on the parameter y. So this is going to be 1 over pi times negative y x squared plus y squared, where y is less than 0 and py is of course a function from R to R. R to R plus, actually, it's non-negative. Okay. always positive. Okay. So then, first of all, I want to claim that this function, I mean, for each y, this function p sub y is harmonic. One could certainly, okay, differentiate it twice and then sum to the result and check the sum. But there's a one-line proof to that, which is you consider this function, which is y plus ix over x squared plus y squared. So this function equals to, if we put up I, which is the imaginary unit, what's left is x minus iy on the top. And for the bottom, it's x plus iy, x minus iy. Then you cancel the common factor, it becomes I over x plus iy. So this is a constant function over a holomorphic function, means it's holomorphic. And this function is holomorphic means both of its real part and imaginary part are harmonic. So we prove that, okay, the function y over x squared plus y squared is harmonic. So py is harmonic. And what's more, we also obtain that this function, let's see, 1 over pi negative x squared plus y squared. This is the conjugate harmonic function to p sub y. So let's assign a name, call it q sub y of x. Okay, so this will be the conjugate harmonic function to this p sub y. Okay, why do I want to define them? Because then I would set f equals to the convolution between p sub y and capital F. And I claim that this is the function that I need. Because first of all, by the definition of convolution, we have that this is going to be f of c integration of r. Okay, I have a knowing constant. And then it's y over x minus c squared plus y squared dz. So whenever I want to this function actually depends on two variables, x and y. So whenever I want to differentiate f, we see that because capital F has neither x nor y, so you always put the derivative onto the last term of the integrand. And we know the last term of the integrand is harmonic. So like if you take the derivative and sum them up, all will be put onto this term, and since it's harmonic, so this function f will be harmonic as well. Okay. And also, we want to check why this is true. So f is defined on the lower half plane, and what I mean by this is when y goes to 0, then the value of fxy goes to capital F of x. So this is true because this set of function is such that the integral of it is going to be 1. That's where the constant 1 over pi comes from. And what else? I also need okay. It's not really support. So okay. So for any fixed ball xr, py of x dx, it is gonna converge to 1 as y goes to 0, and this is true for all r. Means the mass of piece of y is concentrated more and more onto the origin. I mean, onto the origin? Yeah. Yes. Okay. So piece of y is actually a family of approximation identity. And for approximation identities, we have this property that piece of y convolute f will converge uniformly to f. I mean, this x. Okay. Uniformly. Right. So. Oh yes. Of course. That's the capital F. That's the capital F. Right. So in this sense, we say that the boundary value of little f is capital F. So we actually resolved the first question. Right. Okay. I skipped the proof here because probably many. Okay. Question.
Sorry. I'm confused about the property that the interval goes to 1.
Oh, that's one.
What's going on? Because like is the bold center?
Oh, 0.
Okay.
Sorry. Yeah.
So okay.
It's typo. Start Right. Okay. So yeah, I skipped the proof of approximate identity here because I will have a very similar proof later, so I don't want to repeat it again. So you will see how the idea goes for this kind of proof. Okay, so let's go on. Yes.
I'm a little bit confused about how this convolution works, because it seems like it only depends, like, it seems like capital F doesn't really matter, like it just depends on the integral of capital F.
Just depends, yes. Actually, this property does not depend on capital F at all.
Okay.
So as long as your capital F is some function that does not increase too fast at infinity, then this integral will make sense, and then it will be harmonic.
Huh, okay.
Yes. So it doesn't depend on capital F at all. Nice observation. So yeah, and I will actually use this observation later. So okay, that's question 1. So now we have this harmonic extension. We call this little f harmonic extension of the capital F. So then what I'm gonna do is the natural question is our extension unique? So recall that we have this property, and we know this is harmonic on the lower half plane. The question is f unique? Since this is the second question, the answer could be no. And then the reason is you could cook up a new function f tilde, let it be fxy plus y. Then you can see that when you restrict that to y equals to 0, which is the boundary of the lower half plane, this term vanishes. So they share the same boundary value, but like they are different functions, obviously. So it's not unique. But if we put more assumptions onto it, we can actually get the unique harmonic extension. So the assumption we're gonna make is assume f of xy goes to 0 as xy goes to infinity. Then f is unique. So why is that true? Because by assuming this, I sort of unified all the infinity points. So from a topological point of view, you can consider the one-point compactification, and then if it becomes a compact set, and on which you can use the maximum principle on a compact set. But yet to be rigorous, here's what I'm gonna do. So consider a holomorphic function which maps. So the idea is I want to map the lower half plane to a circle. What I could do is, this is negative I. Let's map, say, negative I to 0, and 0 to negative 1, and infinity to 1. And then the corresponding holomorphic function would be hc equals to c plus I over z minus I. Right? If you plug in minus I, it will be 0. If you plug in 0, it will be negative 1. If you plug in infinity, it will be 1. And so this function actually maps the lower half plane to this circle, to this, unit disk. And then, and also you can see that this is actually a biholomorphic function, means its inverse is holomorphic as well. And points converges to infinity is equivalent to a sequence of point converges to 1. And we could this is like one point compactification of that space, and we could define this point, the value of f at this point to be 0. And then f would be like harmonic inside and continuous to the boundary. Then okay, from the maximum principle, principle says, oh, okay, so I'm not sure that this is good for every one of you. So this is saying maximum of a harmonic function on a bounded domain U is going to be, okay, maybe Riemann is always maximum of U. So if there are two solutions, U1 and U2, we consider U1 minus U2, which will vanish on the boundary, and sorry, let me add to that. U1 minus U2 will vanish on the boundary, so this will be 0, so this will be 0, so U1 equals to U2. Right. Okay. So, but like these are all technical points. The idea is like consider the one-point compactification. Right. So we actually have the uniqueness if we assume this.
One question.
Yes.
Is it also true that we assume that f is bounded?
I am not sure. I actually tried before, but I couldn't prove it because in that case you lose continuity, and then you couldn't use the maximum principle. I don't know if there's a way to fix that.
Just wondering the lowest way of says that okay, if on the entire complex plane I have a bounded holomorphic function.
Yeah, that will be constant.
Right.
But
here the half plane like
right, for half plane, what happens changes dramatically, and you will see like later for half plane, holomorphic function can only have negative frequencies, and you cannot. Yeah, I don't think. Yeah, you cannot extend it to the upper half plane. Of course, otherwise it will be a constant. Right. Right. So this resolves question 2. So now we actually have a pretty nice harmonic extension, provided we assume this. Okay, so which can I erase? Okay, I actually want to keep the Poisson kernel and erase everything else. so now the question 3 is the question I mentioned in the abstract, which is, say we have a real-to-real function, well-defined, okay, CC infinity function on the real line, and we have its corresponding harmonic extension in the sense of what I have done above, and we can of course find its conjugate function, conjugate harmonic function, and then can we define? Okay, so the question is really, is this well defined R? So the boundary value of this harmonic function, is it well defined? And what's the relation between F and G? Oh, sorry. I mean capital F and capital G. Right. Okay. And now we've already developed the tool. So let's just compute before I draw the conclusion. So we know F is Qy minus. We know that G is going to be Qy convolute capital F, because we know Qy is the harmonic conjugate of Py, so Qy convolutes whatever function you like is harmonic function of Py convolute that function. So that function actually does not matter. What matters is the kernel. Okay. So G is this up to a additive constant. But we will make sense why we want to choose this later. Okay. So let's say G is this, and then okay, we actually know what it is. So Gx is integral on R. Of course we have those constants. Then what I want to do, okay. Fx minus c, c squared plus y squared dc. Okay. So this is the definition of convolution function. And oh, sorry, this G is depending on 2 variables. And now, because we want to consider its boundary value, so we want to pass y to 0. So the send y to 0, let's first do it naively. So the pointwise limit of the integrand would be fx minus z times y over z, or 1 over z, which unfortunately is ill-defined because y over z is not integrable. If my capital F is not 0, then this would definitely be ill-defined if you should just write something like this. So okay. So here is the miracle, although many of you might have already known. So let's define g of x to be negative 1 over pi principal value of this integral dz. By principal value integral, I mean so this constant, then limit epsilon goes to 0 plus negative infinity to negative epsilon, the same integrand plus epsilon to infinity, the same integrand. So I basically do integral on symmetric domains and then send epsilon to 0. Okay, so I define my G to be this. Of course, then you can expect what follows. I'm going to claim that okay, G converges to capital G uniformly as y goes to 0. Okay. First of all, I'm going to claim this is well defined. I mean, this limit exists, and then I have this convergence. Okay. Then I'm going to prove this claim. Do here. Okay. Let me just continue here. So the clock works. Okay, it works. So the idea is. So let's use some calculus trick. So I want to change the bounds of the integral so that I can unify them into one integral. So negative infinity to negative epsilon x minus z 1 over z dz. By a change of variable, you just flip the sign. It would be negative epsilon to infinity f x plus z 1 over z dz. Because the sign here flips, the sign here flips, the sign here flips. So you flip it 3 times, so there's a negative here, and x minus z becomes x plus z. Okay, so this part goes to this. So like the thing within the parentheses, let me assign a name, g epsilon tilde. Okay, g epsilon tilde of x, y is going to be epsilon to infinity, what is it? Fx minus z minus fx plus z, 1 over z dz. Okay. Okay, so first of all, why does this limit exist? Because if you consider g epsilon 1 minus g epsilon 2, this is going to be less than equals to, let's pretend epsilon 1 is less than epsilon 2. And then what's inside is fx minus z minus fx plus z, then 1 over z dz. And then this is bounded by, this by mean value theorem is bounded by the L infinity norm of the derivative times 2z 1 over z dz. Oops. This is going to be very small, so it converges to 0. So it's well defined. Okay, well all defined, and then I'm going to check the convergence. It's because we've done this change of variable trick and unifying trick to capital G of x. We can do the same thing to the little g. So let me just write it down. It's actually 0 to epsilon. Okay, of course I have that constant. 0 to epsilon. Fx minus z minus fx plus z. This is z squared plus y squared dz. Okay. This is just by a change variable, the same idea. What happens is, then I'm going to write this as, 0 to infinity, not 0 to epsilon. But that's what I'm going to do now. So we write it as the sum of 0 to epsilon plus epsilon to infinity. The 0 to epsilon part is going to be small by the same reason. The same as I did above. And so we want to prove this is close to capital G, and we know capital G is close to G epsilon tilde, and little g is close to this part, so we only need to prove that this part is close to G epsilon tilde. Right, so let's call this part 1. This part 2, we only need to prove 1 and 2 are close because the other terms are small. So 1 minus 2 is going to be, So now I don't have to worry about the constant because I put it out. What's left is, okay, f, so this difference is in common, but what we need to compute is 1 minus z minus the c over z squared plus y squared, then dz. Okay, maybe absolute value on both sides, and then it's basically the same idea, but we need to compute the difference of the kernel. So difference of the kernel is the common denominator z squared plus y squared. Then on the top, it's like z squared plus y squared minus z squared. So it's y squared, then dz here. Right. So then I again use the mean value theorem. I have this Hamiltonian norm of the derivative. What's inside is 2z times z squared plus y squared dz. We can evaluate this integral explicitly. So this actually equals to 2 times f prime infinity. This is like arctangent z, but you have to do a change of variable. So, and there is a multiple, so there is a extra y, because if you like divide everything but by y squared, so this will be 1, and let's see, yes. Then you will have a extra y here, because here you divide y, you have to multiply by y. Okay, so you have this extra y, and what's left is arctangent z over y evaluated at infinity, epsilon to infinity. So this part is bounded, this part is bounded, and y goes to 0. Right, so this goes to 0. So now if you revisit what we done for 3 terms, this goes to 0 regardless of regardless of x, and the other terms are the same. So it actually goes to 0 uniformly. So now this is true. Okay, so now we actually have a way to find what our capital G is, which is, so after having done so many of these, so G of x is negative 1 over pi principal value of fx minus z 1 over z dc. So this is so-called Hilbert transform of capital F at x. So okay, so Hilbert transform formally is defined as f convolute with 1 over pi x. So yeah. Right. So okay. So this is one way to see the relation between capital F and capital G. And there is actually another way, and we can actually unify them to see more interesting properties of Hilbert transform. So let me erase this part because this part is not going to be useful. Okay, the other way is, so now we're going to use Fourier transform. So by Fourier transform, I mean the Fourier transform of the function is defined to be the value of this integral, e to the negative 2 pi this is only defined. Oh, C, right. Thank you. This is only defined for L1 function, but our function is C infinity, so don't worry about that. And the Fourier inversion formula tells us that you can actually write f of x in terms of an integral of its Fourier transform. So this identity is true for these infinity functions. Okay. And why is this useful? Because what we're going to do next is, and also, okay. Having defined for a transform, we have this interesting fact, which is the Fourier transform of the some kernel is defined here, is e to the 2 pi y c. There's absolute value on c, and y is negative. Okay. So this is actually a pretty hard calculus problem, but like if you do the other way around, I mean, assume we have this, then you use Fourier inversion formula to check it. It would be pretty easy. It would be just like some simple complex analysis trick. The other direction is very hard. But yeah, I will not check it. I will leave it for you. So this is
look at the table, right?
what?
There's a table, right?
Table for what?
For Fourier transform.
Oh, yeah, sure. Of course. So why is this useful? Okay. So then, another useful property for Fourier transform is, since our little f is Fourier transform, is convolution between capital F and Py, so we actually have this identity. So this is always true for convolutions. So then now what I'm gonna do is okay. What I mean by f hat is okay. So fxy is f hat cy. So the Fourier transform is only in the x variable, but not in y. It's important. Here. Then e to the 2 pi I x c x c. So this is the Fourier inversion formula. Then I'm gonna plug in the identity here. So this tells us that this is actually f hat of c times py c e to the 2 pi I x c dx. And this is f hat c. Py is e to the 2 pi y c e to the 2 pi x c dc. Okay. So this is for f, for little f. And for little g, we can actually write it in terms of capital G, because little g is the harmonic extension of capital G. And yeah, I probably have to say something about it. So we proved the uniqueness, but under the assumption of like that the function has to go to 0 as variable argument goes to infinity. So this is actually true for little g defined like this. You can check that. It's true for both little f and little g. So little g actually equals to e to the 2 pi I x c dc. So okay, because little g is common extension of capital G. And then Cauchy-Riemann equation tells us f sub x equals to g sub y.
And so is the Fourier transform of q of y also e to the 2 pi y absolute c?
No, you have to multiply that by negative I, something like that.
Okay.
So here the thing is I want to avoid compute the Fourier transform Qy, so you use Fourier transform Py and
Oh,
remove
yours
that.
is symmetry.
I just don't want to do more computations than this. Yeah. Yeah. So now we use the Cauchy-Riemann equation, but the derivative of x is going to be eventually on this term, and that will put out 2 pi I c, right? And I have this f at c. That should be g sub y. G sub y will put out 2 pi absolute c, and then this will be g at c. I equate the integrand because this identity is true for all x and y. So is this clear? Yeah, I skipped one step. So what's happening is if you compute f sub x, you will like have a additional multiplier, additional term like this. And if you compute g sub y, you will have a additional term which is 2 pi absolute c. Of course, here I'm computing fx and g sub y, but they are equal for all x and y. So the integrand should equal, and then I cancel the common factors, and this is what's left. Okay, so then again you cancel like 2 pi thing, 2 pi and the c. You will get that. Let's see. Effect. Which direction do I write? Okay, let's write like this. Then you get I times sine of c f hat equals to g hat. C over absolute c is its sign. So this tells us that, and also from here we know, okay, from this identity, we know that HF Fourier transform is negative G Fourier transform. So, and from there we get this is negative I sine C F hat. So this actually tells us the formula, I mean the multiplier, the formula of Hilbert transform, Fourier transform for Hilbert transform, right? And what's more, you can see that, so yeah, we have this identity and this identity, and also what? Let's see. F hat is negative I sine C G hat. This is again from that identity. So this equals to Hg for a transform. So this tells us F is Hg. So let me summarize a little bit. So this is like another property for Hilbert transform, and we have F equals to Hg, and we also have G equals to negative Hf. So this is the relation I wanted to derive for the imaginary and real parts of the trace function. Okay. And there's one more thing to mention, which is f plus ig of x, y is going to be integral f hat plus ig hat. I'm just like summing these two identity up. Okay, let me recover the original expression. I'm gonna sum them up and multiply this expression by I. So what's the other one? It's like 2 pi c e to the 2 pi ix c dc. Oh, maybe I don't need it. Yeah, I do need it sit here, we know that f hat plus I g hat is just, okay, f hat plus I, g hat is I sine c, so times I again, then sine c f hat. So this is going to be, I squared is negative 1, so this is minus. So this is going to be f hat c times the characteristic function on c less than 0. Right. 2, of course. There is a 2 here. So this means such holomorphic function only have negative frequencies. Right. Oh, okay. So that's all the analysis tool I'm gonna say. So I'm gonna use like 10 or 15 minutes to talk about PD stuff. Okay. I no longer need this Poisson kernel and Harmonic analysis trick. All that we need is on the bottom of the right board. Okay. Now, so I don't want to start from the very beginning of wave equation. So let me jump directly to the equation I want to start with. So for those of you who are familiar with the equation, I'm going to assume, okay, first of all, it's of course 2D, otherwise I can't use complex variable. 2D and infinite depth means like there's a water surface here and the depth is infinity, so we can somehow use the lower half plane and use Riemann mapping theorem to somehow, yeah, you'll see it later. So it's infinite depths. And then, of course, water wave equation, which I will elaborate later. And I'm going to assume all the things that's necessary for mass to be done, which is incompressible, irrotational, the density of water is 1, the gravitational acceleration is 1, and the pressure on the surface is 0. Okay, these are just technical things, it's not important at all. So at the end of the day, the equation will be phi t plus half graph phi squared plus y equals to 0. Gamma t, where gamma t is this free surface moving according to t, and omega t is the lower half plane but bounded by the free surface. Okay, what's this phi here? Phi is the velocity potential. Means, so the velocity uv equals to phi x, phi y. And so this is the velocity, and because of, irrotationality, we can have this velocity potential, and then the velocity potential satisfies this so-called Bernoulli equation, and then you also have this non-penetration condition on the boundary, means like normally the velocity of your water cannot move faster or slower than the boundary. So so that means if this is x of t, y of t, equals to velocity of 0 yt, and the velocity on the boundary is, okay, let's use uv, times the normal on the boundary should be 0. So this is our t squared. Okay, so basically these two equations is what we're gonna consider later. And the way we want to rewrite it in terms of holomorphic variables is the following. So first of all, okay, and then there's one more assumption which is crucial. So we want to assume gamma t. So for all t, gamma t will goes to y equals to 0. Yes, as x equals to plus infinity. Means that the free surface gets flatter and flatter as your x goes to the leftmost side and the rightmost side. So by this assumption, we can actually find a unique biholomorphic function. Let's say f from c minus to omega t, such that okay, so this this curly f is dependent on t, and it's actually x t or y t, right? And if we write ct equals to xt plus iyt, then we claim that curly f actually satisfies zt alpha beta minus alpha plus I beta goes to 0 as what's that? Let's say as alpha beta goes to infinity. So again, this is the reason we have this condition. We can have these nice properties because the same idea as one point compactification. Because you have this nice property at infinity, so you can sort of have still inherit this property when you consider the one point compactification of the lower half space. And so you can assume this. Okay, so here is I know this is a bit confusing. I should explain more. So curly ft is a function from lower half plane to omega t. So it actually has three variables. So f maps t alpha beta to xt alpha beta plus I y t alpha beta. So t is a time variable, alpha and beta, and now instead of x and y becomes my new complex variables. Yeah. Okay. So okay. Let me erase all of them. I think. I'm gonna delete them. Okay. So then let's see. What do I want to do next? Okay. So then there's a lemma which is very useful when computing this kind of spatial change of variable, which says so we have two functions fg and f. So okay, let's do it like this. G is a function from c minus to r. F is a function from omega t to r. And G is f compose curly f. Right, curly f of t. Yes, okay. These the penalty as well. I should not skip them. So G of t, f of t. So this is f t dot. So then we have the following, which is ft equals to gt minus, okay, let's also assume j is x alpha squared plus y alpha squared. Recall that x is the real part of mapping here. Y is the imaginary part of mapping here, and I can take derivative with respect to alpha. So that's what it means. Okay, so then I have this formula for time derivatives. X alpha xt plus y alpha yt g alpha minus 1 over j negative y alpha yt x alpha yt g beta. Okay. So what follows will be a lot of computation, so I'm not going to do them all. I'm only going to like introduce the idea and present how it could be done, but I'm not going to do it because there are too much of them. Okay, the idea is
Excuse me. So what does this x alpha mean?
x alpha. Okay, so x is the mapping defined here. So first of all, I have this holomorphic function which depends on t from the fixed complex lower half plane to the free domain. I mean the free domain. Yeah. Okay. And then okay, because this is a holomorphic function, we have the real part and complex part. So x real part, y complex part. So xt actually maps the complex lower half plane to the Euler variable x.
And that's the
Yeah.
partial.
Yeah. So that's the partial derivative.
Is alpha beta kind of like initial state?
No, alpha beta are just the complex variables. So the idea is, of course, this is a free boundary problem. So we want to somehow change it into a fixed boundary problem. So that's one of the main idea of doing this.
I mean, it looks like xt alpha beta and yt alpha beta. It kind of looks like we have initial like point alpha beta, and then we are kind of looking at the trajectory of alpha beta, like xt and yt. I mean.
Yeah. So this change of coordinate depend on t. So alpha beta are like fixed variables. They're going to be our free variables, and then x, y are like holomorphic functions or harmonic functions depending on alpha beta.
Because domain is changing, we are fixing one point, and then we are.
So by this change of spatial coordinate, now the domain is fixed. It no longer change at all, right? Yeah. So that's the main purpose of doing this. And then okay, why is this true? Okay, I'm not going to compute it, but the idea of deriving that is from this identity here, we actually have g alpha. Recall that g is a function dependent on t, alpha, and beta. G alpha is fx x alpha plus fy y alpha, chain rule, right? G beta equals to fx x beta plus fy y beta. By the Cauchy-Riemann equation, x beta is negative y alpha, y beta is x alpha. And then this is a linear system for fx and fy. We can solve them. So x alpha, y alpha, negative y alpha, x alpha, fx, fy. The determinant of this matrix is J. So if you invert it, you will get fx, fy equals to 1 over J okay, they're both alpha, so I don't need to change them. I guess this is in the negative y alpha, then g alpha, g beta. So this is just the inverse of that matrix. Right, so this is how you change from between x, y, and alpha, beta. And to do the time change, I mean the relation between time derivative, we consider gt should be by chain rule ft plus fx xt plus fy yt. For fx and fy, plug in what you get from above, and that what you get. Okay, yeah, this is the standard thing you would do for change of spatial variables. Okay, let me erase that. 10 more minutes. Okay, well, what's left is like purely copying down stuff, I think. So, okay, another idea. Okay, so now we start the computation on the function. So, first of all, we still have to introduce more notation. So phi of t is, let's assume it's psi equals to phi t dot composed with f of t. So this is a function dependent on alpha beta. This is function dependent on x and y. Right. So because uv equals to phi x, phi y, this is from our equation there. You can use the lemma here to compute phi x, phi y, right? Because this is exactly the same as the identity we have in the lemma. So it's 1 over j x alpha phi alpha minus y alpha phi beta. Okay, that's for you. V is 1 over j y alpha phi alpha plus x alpha phi beta. There should be a parentheses here. Parentheses. Okay. And then also x minus alpha plus I y minus beta is holomorphic. So x minus alpha is Fourier transform of y. Y is negative Fourier transform of x minus alpha. You see that beta goes away because once you restrict it on a boundary, beta is 0. Yeah, so this is the relation between that, and then by the Cauchy-Riemann equation, phi beta restricted on a boundary is so cool. I have to introduce one more notation. Maybe too much notation? Okay, I have to do that. So let Q be phi plus I theta. This is a holomorphic function. So basically I find a harmonic conjugate harmonic function to psi and call for the whole thing Q. And then if I have this notation, then psi beta, I can represent it using Cauchy-Riemann equation. It's beta alpha restricted to beta equal to 0. So we always use the capital letter to indicate the boundary value. So capital theta alpha. Okay. Okay. I don't need this. Since I don't really have much time left, and I think it's probably too complicated to go through the computation, so I'm gonna tell you what the result of first step is, and yes.
Can I ask a quick question?
Sure.
So do we also know that the partial derivatives of the function go to the partial derivative of the function of the boundary?
So yeah, so beta the derivative
No, the
should not.
derivative is in alpha.
Oh, yeah, this should be okay. Yeah, that's a good question. So I did not prove that. Yes, indeed, but I guess for single integral operator there is W1P to the W1P boundiness of properties. I guess you meant to did the proof in the working group. Right. Oh, okay. So. Yeah, but there should be property like that, so you can extend it to the right. So, but yeah, at the beginning you can assume everything is smooth and first see the idea of like what the structure will be from there. Okay, so let me tell you how the result. So let's call this star. Let's call it star star. Then star star will it gives you Ct plus f C alpha is 0, where Z is just x plus I1, the boundary value of this, and f is a holomorphic function defined by theta and j. So this is the imaginary part, and then you consider Hilbert transform, it becomes a holomorphic function. So that's what star star is. And star will give you Qt plus fq alpha plus q alpha square over 2j minus h q alpha square over 2j equals to I times z minus alpha. So this is a holomorphic function, right? Oh, I might miss an I somewhere. There should be an I here. So this is a holomorphic function. This is a holomorphic function. Q is the boundary value of this little q, and yeah, so that's what star is. So these two together gives me the holomorphic version of what a wave equation. This is fully nonlinear to further derive like estimates and prove all sorts of existence uniqueness. The standard technique is you can differentiate once more to get a quasi-linear system, and then by some other fancy change of variable, you can actually do something with it. So if you're curious about like what's after this step, I can give you some reference later. Yeah. So that's basically it. But like the whole point for a free boundary problem is always if you can change it into a fixed boundary, that's already a great step. So the most important point is now the boundary is fixed. I mean, now the domain is fixed, and then this equation, although very complicated, is doable. It's a pretty recent paper, 2014. Yeah. So that's all on time. Thank you.
So do you guys have any questions or comments?
Yes.
So it seems like the complex analysis technique is like a fancy way of change of variable that encodes the harmonic constraints.
Right.
So like, can we do it on like not the infinite depth water wave, but just like bounded water wave, and like we do some complex analysis between two horizontal planes.
Right.
Get some similar results.
If it's finite depth, then there will be conditions on the bottom, and you have to encode those conditions into the holomorphic expression of the equation, and I guess that can only happen when the boundary condition is really nice. Otherwise, it's going to be very hard. Yes, I did not do the technical proof here, but actually to derive this property, you have the rigorous proof will be like you have to go back to the circle again, and somehow find the Riemann mapping from Riemann mapping theorem. And Riemann mapping is like essentially unique. If you fix some point and fix some angle, and then if you go back, you will have this property. But this strongly relies on the fact that we have this vanishing property at infinity. If you have the bottom, you will make sure all those boundary conditions like satisfy some I don't know some nice equality, so that you can rewrite it in terms of holomorphic variable. I don't know how. Yeah, I'm not sure. I haven't tried.
Any other questions? Alright, let's thank you again.
From what I understand, if you have finite graph, the natural like boundary division is constant there. And I'm looking at this kind of harmonic function.
So we just not.
I'm not sure. Maybe I'm not sure.
Yeah, the natural boundary.
Maybe I'm not sure.
后面就是继续那个，因为
Yeah.
但还有别的作用，但我觉得别的作用发哨作用就是它有别的作用，但别的作用发哨多过实用，这是比较实用的一方面。再是对 ，pure transform 有一些比较好的 property，比如说它 it always maps LP function to LP function。对，so it's a bounded limit to LP and more of it's bounded limit。W1P 对 W1P， 这个是去年这个时候吧？我评估你不是证了的 W1P 到 W1P 的 boundedness。对。这就是 single operator 呀，然后你当时不是证那个 W1P 的 W1P boundedness。对，我证。对，我刚才说这个。